Section 4.9, Mechanical and Electrical Vibrations. This is also under the title of Linear Dynamical System. It's the application of second-order homogeneous linear ordinary differential equation with constant coefficients. You can see these applications in spring problems, pendulum problems, and electrical circuit problems. Spring mass system. So these are the type of problems we will go over and develop some formulas and differential equations for them. And first, we will examine free undamped motion. That means that there is no drag force. In other words, there is no external force which will reduce the oscillation of the system, because these kind of systems are known as harmonic systems, and these are the type of system which you can they create oscillations. So as far as the damping is concerned, so let's just define that quickly. And that's damping is the influence within or upon an oscillatory system that has effect on reducing and restricting or preventing its oscillation. So whatever it is that restricts the oscillation or slows down the oscillation of a system is known as drag force. A prime example of a drag force could be air resistance, or it could be like if you put a spring inside, let's say, a bucket of oil. So here is the scenario. Suppose you have a spring which is attached to somewhere. So this is the natural length of the spring. So we're going to denote that by L. Now we're going to attach a mass to it. So it's going to oscillate due to the gravity. And eventually it's going to go up and down, oscillate, and come back and stay in one point. That point is called equilibrium point of mass at rest. We're going to assume that if the mass goes above the equilibrium point, you have negative displacement, and below it is positive. So positive direction is downwards and negative direction is upwards. So some definitions. D stands for displacement of the spring from its equilibrium position. It could be the stretch or compress, the amount of deflection. X sub t is the position of the object or mass at any given time. And excuse me, X is equal to 0 is the equilibrium position of the system. So right here, X sub t is equal to 0. Now, before we go over some problems, let's make sure we understand the units. Also, D plus X, if you apply an external force to move this mass, so that's going to be what? You're going to add amount of X to the amount of deflection. Remember, deflection is amount of stretch or compression of the spring. So spring has been stretched this much, so that's deflection. And when then it goes up and down, that's extra distance, which is called X. So therefore, the total distance, displacement of the spring from its natural length is D plus X. Before we go over some problems, let's quickly review the units. If the you can have units of force, mass, and gravity in engineering system, in MKS, which stands for meter, kilogram, seconds, and CGS stands for centimeter, gram, and seconds. If force is in pounds, mass is measured in a slug, that's SLUG, and G is 32 feet per second square. If force is measured in newtons, mass is in kilogram, and G, the gravity is constant, is 9.8 meter per second square. If F is measured in terms of dynes, that's how it's pronounced, mass is gram, so gravity is 980 centimeter per second square. So F is force, M is mass, G is the constant of gravity. So keep in mind, if what? If the mass is above the equilibrium point is negative, below is positive. Because we're dealing with spring, so let's review quickly what Hooke's law is. Hooke's law says the amount of force exerted by the what? Spring is proportional to the amount of deflection, where K is called constant of what? Spring. So in other words, spring is trying to go down, but what? Due to the gravity, but it's going to be pull up, and the amount of force is proportional to what? The amount of deflection with a negative sign, because you know spring is trying to go down, but due to the gravity, but it's pulling up by the amount of the force due to the spring. The forces on mass are weight of the spring, which is mg, that's due to the gravity. Spring force, which is what? Minus k times d plus x. Keep in mind, when you apply an external force, then what? Then the mass, in addition to its deflection, it also has to have to go x many units above or below what? Equilibrium position, depending whether you stretch the spring or you compressed it. So that's what this is. And we have no damping forces at this point, so no external force is going to reduce what? The speed of the oscillation. So we are not going to worry about that for time being. Maybe that comes up in part 2 of this video. The question is, what happens at equilibrium? And what is equilibrium position? That's where the system is static mode. That means the forces must exactly balance each other out. In other words, the summation of the force due to the gravity and the spring has to add up to 0, which means f of g has to be negative fs, but fg is the weight of the spring, which is mg, and that's minus kd, so mg is equal to kd for what? K times d, when the force spring is in what? Static mode, which means it's at equilibrium point. However, the minute you what? Exert an external force and what? Push the mass, let's say, downwards, then the Newton's law of second law of motion kicks in, which is ma. So what happens is ma would be equal to minus fs plus fg. Remember, g is the gravity going down, but the force due to the spring is pulling the spring up, or this mass up. So these guys always have opposite what? Signs. But remember, Fs was the same as what? Minus k times d plus x, correct? And then plus mg, right? So now, if you distribute, you get minus kd minus kx plus mg. But remember, mg is the same as kd, so these guys cancel. So all you get is m, the second derivative of the position function with respect to time, which is acceleration, a, so this is a, equals negative kx. If you move that kx, k is the constant of spring, to the left side of the equation, set it equal to 0, you get m second derivative of what? Position function with respect to t plus kx equals 0. So this differential equation, second order differential, homogeneous differential equation, describes the behavior of the mass, you know, under just gravitational force. In other words, no other external force is involved. In other words, the experiment is done in a vacuum, so we are neglecting the air resistance. In physics classes, x dot is dx dt, x double dot is what? Second derivative of x with respect to t, correct? So that's just notations they use in physics. So basically what we do, we divide both sides by m, the mass, so we get this. We let this guy k over m to be equal to omega squared. So this notation is omega. So we're going to let that k over m, which is constant of a spring divided mass, to be omega squared. What is omega? Is angular frequency of the system, which is measured in terms of radians per second. It's also known as circular frequency. Okay, so therefore omega is the square root of k over m, and omega is related to natural frequency by this formula. Omega is equal to 2 pi times f. F is what? The natural frequency, okay, which is pretty much like 1 cycle per second. That's like the number of oscillations per unit time. And the unit for F is hertz, okay, is hertz. Whereas the unit for omega is radians per second. So that's basically how the equation gets to be developed. Let's say we have the initial conditions x of 0 is x0 and x prime of 0 is v0. In other words, this is the initial position of the mass. This is initial velocity, with x0 being positive. So what happens is when you solve this second order homogeneous differential equation, the auxiliary polynomial becomes r squared plus omega squared. So r is plus or minus omega I. So we got complex roots. Remember, this is the case where there is no damping force. So the solution will be linear combination of what? Sine and cosine. So the position of the mass at any given time is given to you by, let's say, C1 sine of omega t plus C2 cosine of omega t. But usually it's customary that we use A and B as opposed to C1, C2. However, the period of the motion, motion is defined as 2 pi divided by omega, which is seconds. And natural frequency is reciprocal of the period, and the units is hertz. So in case you have that kind of equation, the amplitude is what? Is the square root of a squared plus b squared. So the amplitude, A stands for amplitude, okay? How far the object goes up and down, the maximum or minimum height. That's square root of a squared plus b squared, which is the same as the square root of c1 squared plus c2 squared if you use the constants c1 and c2. However, if you only have one term, that means one trig function, like let's say 2 cosine of 3t, then the amplitude is the coefficient of the cosine, okay? And amplitude cannot be negative. So in this case, if you have negative 4 sine 3t, the amplitude is what? 4. So basically, if these are the initial conditions and that's the general solution, we always look for particular solution. So we need particular solution. General solution doesn't have any purpose in this kind of word problems. So after you impose what? Initial conditions, x of 0, x0, x prime of 0 is v0, you end up with b is equal to x0 and a is equal to v0 divided by omega. And this is how what the position function for the mass looks like at any given time. Keep in mind the coefficient of t when you looking at the argument of the sine and cosine is omega. And period is what? 2 pi over omega. And omega, if you recall, is defined as square root of constant of spring divided by mass. Excuse me. For example, if you were going to solve x double prime of t plus 16 x of t equals 0, with the initial conditions of this is initial position and this is initial what? Velocity. If you impose these conditions to the solution of this differential equation, a0, b comes up to be equal to 10. So the position of the mass at any given time is 10 times cosine of 4t. So the period is 2 pi divided by omega. Remember, omega is the coefficient of t in your theta. So that's pi over 2 seconds. Reciprocal of this is what? Frequency, which is hertz. And amplitude is absolute value of this coefficient, which is 10. And as I said, omega, you can find it by inspection. That would be like what? The factor of the t when you're looking at the argument of the sine and cosine. So let's just make some comments about the initial conditions, then we'll go over a problem. So mass is released from rest. So when you see this statement, mass is released from rest, that's just like x1 is equal to 0. What was x1? That was like initial velocity. Okay, remember we decided what? X of 0 is equal to x of 0 and x prime of 0 is equal to v sub 0. And in this case, we like this guy to be denoted by x1 and this guy denoted by x0. So that's like at time 0. Initial velocity and initial displacement. If initial displacement is positive, but initial velocity is negative, mass starts from a point below the equilibrium position with upward velocity. So keep that in mind. Initial displacement is positive, initial velocity is negative. That means mass starts from a point below the equilibrium position. If x1, which is initial velocity, is 0, mass is released from rest. So make sure you know these terminologies. If initial displacement is negative, but what? Initial what? Velocity is 0, mass is released from rest from a point absolute value of x of 0 units above the equilibrium position or point. So basically this is how the equation or the solution of second order differential equation looks like when we're talking about these kind of problems. And incidentally, these kind of problems fall into a category of problems called harmonic motions. Basically what that is like what? You have a system which creates what? Oscillatory motion. Period is 2 pi over omega and f is reciprocal. So with that said, what do you say we kind of look at a simple example and then go from there. Suppose the question is, spring is stretched 2 inches by a force of 16 pounds. An object weighing 4 pounds is attached to the end, is pulled down 3 inches below the equilibrium position and released. Find the subsequent motion and find the period and frequency and the amplitude of the resulting what? Motion. To begin with, we know the force due to the gravity is equal to mg. So in this case, we have a weight and an object weighing 4 pounds. So g is equal to 32 feet per second squared. So we can find mass, which is 4 divided by 32. That's 1/8 slugs. 2 inches first has to be converted to what? Feet, because you cannot have inches. So that's 1/6 of a foot. And then force due to the spring is equal to K times D. So in this case, a 16 pounds of force stretched the what? Spring 2 inches. So 2 is the deflection, which in feet, it's 1 over 6 foot. So 16 equals K times 1 over 6. So the constant of what? Spring is 96. Here is the equation, differential equation for an undamped motion. So there is no damping force involved. So that's the equation, rain or shine. Replace the m with 1 over 8 and k with 96. Auxiliary polynomial is 1 over 8 r squared plus 96. So the roots of this differential equation is plus or minus 16 square root of 3i. So you get pair of conjugate what? Complex roots. So the solution to that differential equation is C1 cosine of square root of 16 square root of 3t, C2 sine of 16 square root of 3t. But now we need to impose the initial conditions to find these constants, correct? Because this kind of solution is not acceptable in real life. In real life, we always look for what? Particular solution, correct? One of a kind. It says right here, an object of 4 pounds is attached to an end, is pulled down 3 inches below. 3 inches is quarter of a what? A feet. It's below the equilibrium point, so it's positive 0.25 feet. That's your initial position. And the catchword here is released. That means the initial velocity was what? 0. So these are your initial conditions. So initial displacement was positive 1/4 of a feet. Initial velocity is 0 because notice it says and released. Okay, impose those conditions and you get C1 is equal to 1/4, C2 is 0. So you get this equation as your solution. There goes the particular solution for this problem. Do you see it? Now I can find the period, which is 2 pi over omega. Remember, omega is this factor. So that would be 16 over 2 pi over 16 times the square root of 3 seconds. That's the unit of period. Amplitude is what? Absolute value of this coefficient, 1/4. Frequency is reciprocal of the what? Period, which is 16 square root of 3 over 2 pi hertz. So this is natural frequency, that's angular frequency. Okay, so in the next video, we talk about what happens if you have drag force, which is more realistic than this one. This experiment assumes the entire experiment is done in a vacuum, but you know, in real life, you gotta have, if nothing else, the air resistance as your drag force. Thank you.